Good morning, guys. So today in this lecture we are going to see the finite elemental analysis procedure for trusses or finite elemental analysis for truss element. Okay, so in previous lecture we have discussed about one dimensional bar element. In the previous lectures we have discussed about how to solve the one dimensional spring element problem, how to solve one dimensional bar element problem, how to apply the steps, that is a finite elemental analysis steps to these one dimensional spring element as well as bar element. Now in this lecture we will see what is the procedure or how to solve the truss problems by using finite elemental analysis. Okay, so how to solve the truss problems by using finite element procedure. Okay, so in this lecture we will see the FEA for trusses. Okay, so basically what do we mean by truss? So first thing is, what do we mean by truss? So truss is nothing but it is a structure which is composed of elastic members. Okay, this is nothing but a structure like this. It is nothing but a structure which is composed of elastic members and on which the elastic forces are acting. Okay, so truss is nothing but a structure which is composed of a elastic member on which the forces will be acting. Okay, now we will see actually, as we know that in your strength of material theory, you know that what we mean by determinate structures and indeterminate structures. Okay, so determinate, it means if the number of unknowns are less than or equal to the number of equilibrium equations, then such type of structures are called as determinate structures. And if the number of unknowns are greater than the number of equilibrium equations, then such type of category is called as indeterminate structure. So we know that equilibrium equations means what? Summation of H is equal to 0, summation of forces in horizontal direction, forces in vertical direction, it must be equal to 0. Also summation of movement about end point is equal to 0. Okay, so these are three equilibrium equations. And if the number of unknowns in the structure is less than or equal to the equilibrium equations, actually here the equilibrium equations n is equal to 3. If the number of equations are less than or equal to 3, then you can call it as a determinate structure, or such type of category is known as determinate structure. And if the number of equations, number of unknowns is greater than this number of equilibrium equations. Now number of unknowns means what? Reactions, displacements. If this number of unknowns are greater than this number of equilibrium equations, then you can call such type of structure as a indeterminate structure. Okay, actually you have studied these concepts in your strength of material theory, or you can study it in your first year in mechanics. Okay, now we will see the finite elemental procedure, how to solve truss problem by using a FEA. Okay, so see, this is the truss problem. Okay, there are three members, 1, 2 and 3. So from this truss problem you will come to know that each member has different axial direction. Okay, so for this member, its axial direction is what? This is the axial direction. For this member, axial direction for this member is like this. And for this member means this is horizontal, this is vertical, and for this member it is inclined to some reference point. If we take this line as a reference line, then this member is at angle theta. So its axial direction is like that. Okay, so every member has different axial direction. But in our previous lectures, we solved the examples related to your one dimensional bar element. in which the axial direction is same, which is nothing but horizontal. Means displacement will be occurring in this horizontal direction. But here in this case, the displacement will be different, will be occurring in different directions. Means for this member, it will be occurring in this direction. For this member, it will be occurring in horizontal as well as in vertical. So we need to take some reference point or some reference coordinate system, which is known as your global coordinate system. Okay, so this is your local coordinate system. So we need to convert this problem into our global coordinate system. Okay, why? Because all members has different axial directions. So we need to convert these axial directions into one global axial direction or global coordinate system. Okay, so for example, we will take this inclined member for our finite element FEA analysis. Okay, so we will take this inclined member for this FEA analysis. So here we are taking this inclined member for our FEA analysis. Okay. Suppose this is your first node and this is your second. Okay. So as we know that the axial directions or axial displacements, it will be occurring in this direction only. Okay. Suppose this is your U1. U1 is the axial displacements occurring at node 1. U2 is the axial displacements occurring at node 2. This is your U. But as we know that the axial directions for every member is different. So we need to convert this system into global coordinate system. So we need to, so first from this figure we can write our nodal variable vector for this bar or for this element. We can write our nodal variable vector as U is the nodal variable vector, which can be written as U1 U. For first node U1 is the displacement, for second node U2 is the displacement. And we know that only axial forces are acting on the element, so there should not be any bending of this truss element. Okay, there should not be any type of bending will be occurring in this element. Okay, only axial forces will be acting on this element because this truss structure, these joints are pin connected joints. So that's why there will not be any bending in the truss element. Okay, so this nodal variable vector, this is nothing but nodal variable vector. Okay, so nodal variable vector which can be written as U1 U. Now we need to assume one global coordinate system. Let us say XY, X and Y is the global coordinate system. So we need to apply our global coordinate system at each node. So suppose this is your X, this is your. Similarly, we need to take the global coordinates. These are the nodal coordinates or local coordinates. We need to take the global coordinates like U1 is the global coordinate in X direction and V1 is the global coordinate in Y direction. Okay, so we need to convert this local coordinates into our global coordinates U1, V1. Okay, so for this, from this figure only we can find out the, let us say, this displacement's value up to this, if this u1 is the total displacement up to this point. So if we, okay, so this displacement in global coordinate, this will be the v1 and this will be your u1. u1 is the global displacement in x direction, v1 is the global displacement in y direction. Now we need to find out this u1, small u1. From figure, if this is the theta, so let us say this A, B, C. So if we make some adjustments, okay, so this is your, we can actually, we have drawn the perpendicular. Okay, so from this, let us say A, B, C, and this is our target is what? Our motive is what? To find out the value of u1. Now u1 is what? This distance plus this distance. Let us say this distance is A and this distance is B. So up to this is A, and up to this is B. So if we take this triangle, so from triangle ADC, so from triangle ADC, from triangle ADC, this is your 90 degree angle. So from this triangle ADC, this is angle theta, and this value is AC is nothing but your u1. This AD is nothing but small. Okay, similarly, second angle, this is second angle, DBC. So from this is your V1, this length is B, and this is your rectangle, I mean 90 degree angle. So if this is theta, this is 90 degree, this angle should be equal to 90 minus theta, then it should be equal to, this total is 90, so it will become theta. This angle will become, okay, so from this figure we know that this small u1 is nothing but A plus B. Okay, so u1 is equal to, now from this diagram we know that cos theta is equal to adjacent divided by hypotenuse. So adjacent is what? A divided by hypotenuse is what? u1. So A will become u1 cos theta. Similarly, from this diagram, sin theta, if you take sin theta, you will get sin theta is equal to front divided by adjacent. So front is B divided by V1. So B will become V1 sin theta. So in this way, you will get U1 as A plus B. So A is nothing but U1 cos theta, U1 cos theta plus V1 sin. Okay. So in this way, you will get U1 cos theta plus V1 sin theta. Similarly, if we apply same procedure to this coordinate also, so here this is nothing but your U2 displacement and this is nothing but your same procedure to this coordinate also, you will get u2 as u2 cos theta plus v2 sin theta. Okay. So in this way, we have determined u1 and u2 in global coordinate system. Okay. So you will get u1 is equal to capital U1 cos theta plus capital U1 sin theta. Similarly, you will get u2. So we can write this u1 and u2. So you can write u1 and u2 as in matrix form. You can write this u1 and u2 in matrix form as so u1 u2 is equal to, let us say suppose now suppose cos theta, let L is equal to cos theta and M is equal to sin theta. Then this will become u1 is equal to L cos theta, replace this cos theta by L and replace this sin theta by N. Okay, so this will become u1 into L plus v1 into N. Similarly, this u2 will become this capital U1, capital U2 into L plus V2 into N. Okay. Here we have replaced this L, this cos theta by L and this sin theta by L. So, if we write these two equations in matrix form as, so we can write these two equations in matrix form as, so we can write these two equations in matrix form as u1 u2 is equal to, now we can write u1 as u1l plus v1l plus u2 0 times u2 plus 0 times v2. Similarly, here we can write 0 times u1 plus 0 times v1 plus these all terms. So we can write u1 and u2 in terms of matrix form as this u1 it will become L M 0 0 times u1 v1 u2 v2. Similarly, u2 will become 0 0 0 0 L N. So if you can read this first u1 equation, then you will get u1 is equal to L times u1, L times u1 plus M times v1, M times v1 plus 0 times v2, 0 times v2 plus 0 times v2, 0 times v2. Similarly, v2 is equal to 0 times u1, 0 times u1 plus 0 times v1, 0 times v1 plus L times u2, L times u2, look, L times v2 plus M times v2 plus M times v2. So in this way, you can write these two equations into matrix form. So let us say this as the, let us consider this matrix as L matrix. Okay, so you can write, this is nothing but your nodal variable vector, small u is equal to L times capital U. This is nothing but your global vector, global variable vector. So in this way we can convert our nodal variable vector into global variable vector by using this L matrix. Okay, so now similar to this nodal variable vector is converted into global variable vector, or you can convert this, you can write 1 minute, or our main target is we need to find out our global variable vector. So global variable vector can be written as now L transpose into local variable vector S1. So this will become a transpose matrix or RHS. So this global variable vector U, capital U is equal to L transpose into small u. Now similar to this, we can write the force relationship. So we can convert our local force vector into global force vector by using this L matrix, capital F. Okay, means what? This is your F1, this is your F2, this is your F3, this is your F, or you can write F1x, F1y, F2x, F2y also, because this force in x direction, this force is in y direction. Similarly, this force acting at node 2, it is in x direction, this force acting at 2, it is in y direction. So F2x, F2y, F1x, F1y. Okay. So you can write similar to this nodal vector variable relationship, you can write our force vector relationship. Now so here we have two relations. First one is U is equal to L times capital U, and F is equal to L times capital F. Okay, where L is the L, it is the matrix, and this matrix is nothing but equal to L and 0, 0, 0, 0, L. Okay. Now, next is what? Suppose this is equation 1. Suppose this is equation. Okay. As we know that for this bar element, the elemental stiffness matrix is given by formula K is equal to, actually we have derived this elemental stiffness matrix for bar element, it is nothing but A by L in bracket 1 minus 1 minus 1 1. Okay. So we know that the elemental stiffness matrix for this bar element is given by A by L 1 minus 1 minus 1 1. Now next is what? 1 minute. So next we need to convert this local coordinate system or nodal vector variables into global system. So for this we know that the force and displacement relationship, it is given by formula F is equal to A by L in bracket 1 minus 1 minus 1 1 into U. Okay, where F is for this element F1, F2, where U is, it is the nodal variable U1, U. As we know that for bar element we can write our force force and displacement relationship by using this equation. F is equal to AE by L into 1 minus 1 minus 1 1 into this. Now from equation 1 and 2 we can write F and U. Okay, so from this second equation we can replace this F by L into F. So from second equation we can write L into this capital F. Because why we are converting this? Because we need to convert this local system into global coordinate system. So we are converting this equation for this bar element equation means force and displacement relationship of this bar element globally. Okay, so F is replaced by this value L into F. Now is equal to AE by L in bracket 1 minus 1 minus 1 1 into, now this small u is it should be replaced by using first equation, means L times capital L times A. L times, okay. So here we need only force vector on LHS. So this will be, it can be written as F is equal to L transpose into A by L. Okay, this L and L will not be cancelled. You cancel L and L cancel because this is the multiplication of these two matrices. Multiplication of these two matrices. So cancel so it should be L transpose into A by L into 1 minus 1 minus 1 1 into L into U. Okay. So from this you will come to know that this is your global force vector. Now this is your equivalent stiffness matrix for truss element into your global displacement vector. So this is your global force vector, this is your global stiffness matrix, and this is your global displacement vector. So global stiffness matrix is nothing but L transpose into A by L into 1 minus 1 minus 1 1 into this L. This is the global stiffness matrix. Now we need to find out this global stiffness matrix by simplifying this multiplication. First we will do this multiplication, then we will do this multiplication. So you will get global force vector is equal to global stiffness matrix into global displacement vector. Okay. So in this way you will get the global in this way you will get the global stiffness matrix. So our target is what? To find out or to get the global stiffness matrix. First we will multiply by this matrix into this matrix, then this matrix to this one. So our next target is what? So similar to our bar element, our new equation will come out. Means for this new equation only this global stiffness matrix is different, because we need to now solve this to solve this equation or multiply by we need to do multiplications to these 2 to 3 matrices, then you will get the global stiffness matrix. So similar to the spring element, similar to bar element, here we will also get a one global stiffness matrix for truss element. Okay, so for spring element our global stiffness matrix was K minus K minus K. Then this is global stiffness matrix for element only, one element only. Actually this is the stiffness matrix for truss element. It should be the stiffness matrix for truss element. So this is the element stiffness matrix for spring element. Then A by L into 1 minus 1 minus 1 1. This is the element stiffness matrix for your bar element. Now the stiffness matrix stiffness matrix or element stiffness matrix for your element stiffness matrix for your truss element is nothing but L transpose into A by L 1 minus 1 minus 1 1 into L. So this is the element stiffness matrix in global coordinates for truss element. So we need to do some multiplications. Yes, so this A equality will be equal to L transpose. So L transpose like that. A by L into 1 minus 1 minus 1 1. This L is nothing but L M 0 0 0 0 L M. Now we need to write down the transpose of this matrix here. Transpose of this matrix is nothing but L M 0 0 L M. See, transpose means what? First row will become your first column. Second row will become second column. 0 0 L M into A by L 1 minus 1 minus 1 1 into this matrix. So in this way you will get the element stiffness matrix in your global coordinates for truss element. Okay, so by solving this or by multiplication you will get the final element stiffness matrix for your truss element. Okay, so up to this clear. Okay, so this multiplication part we will do in next lecture. Okay, so up to this you will get the element stiffness matrix for your truss element. In next lecture we will do some multiplications. We will do multiplications and we will get element stiffness matrix for truss element. Okay, so here I will conclude this lecture, and in next lecture we will start from this part. Okay, so thank you.